where's everybody else?
I thought someone would be here.
Oh, no problem. Huh?
I thought someone would be here.
Yeah, so did I. Anyways, we'll just have to start without them. We'll do current carrying conductor. We'll go through the answers for that now, okay? And then we have to do. Well, we might as well do a few lessons. Do you have a spare pen I can borrow? Thank you. Let's see. Yeah, super. Okay. And you might need your calculator too. Right. Okay. Oh, come on, Ken. There you go. Right. A copper wire carries 4 amps of current. The copper runs through a magnetic field so that the copper is perpendicular to the field. The copper is 40 centimeters long and has a flux density of 6. What's the size of the force? So that one there is F bill, yeah. Yeah. That's 6 times 4
Times 1.4.
yeah. Oh dear. What's that now? Oh my goodness. Sorry. 24, 2.4, 9.6?
Yeah.
9.6 newtons then. And the only difference for the second part is if it makes an angle of 70. So what's that? Bill sine theta, isn't it?
Times, yeah, sine.
So it would just be 9.6 times sine 70. So what did you get for that?
9.02.
9.02 newtons. Alright, that's fine, isn't it? Okay, let's have a look at the next one now. 2. A DC motor is used to turn a wheel. Current of 2 amps runs in it. Flux density 6, 2000 turns, square of 30. What's the torque? Okay, so the torque is I-band.
Yeah.
And the I is 2, the B is 6, the A is 0.3 squared, and the N is 2012. So that's 24,000 times 0.09. What did you get here for the answer?
2160.
2160.
Yeah.
For sure?
Yeah, this is
I'm not sure about the decimal point.
because it's exactly what I thought.
Okay. 2160 newton meters then. 2160 newton meters. Okay, 3. A coil is wrapped around an iron rod of radius 10, 200 times. What's the flux linkage? So that's equal to MBA. The N here is 200, the B here is 3, and the A is pi,
0.1 squared.
yeah, 0.05. Oh no, 10, sorry, I say it's radius, 0.01 squared. So that would be 600 pi times 0.01. So what's that? 6. Oh, and then square, yeah. 6 pi. So this is like about 1920. Hey, what happened to you?
18.8.
Huh?
18.8.
18.8 webers. Let's pause for a second. Let Matt catch his breath. Were you working last night? Yeah, I know, right? February. Yeah, it's normal. Yeah. We're going through tutorial now, Matt. So we're on current carrying conductor. Okay, that's 3A, now 3B. So the only difference is the angle is 20, isn't it? So that would be 18.8 times cos 20. What did you get for that then?
17.7.
Say again, sorry?
17.7.
17.7 Webers. Okay, number 4 now. Student makes a homemade DC motor as shown below. The most powerful magnet they could buy was a 1480 millitesla magnet. A 1.5 volt battery provides an amp of current, and the area is 5 by 5. The N is 1. Compute the torque. Okay, so that's fine. That's just IBAN. Although the N is 1. So what's that? I is 1. B is 1.48. A is 0.05 squared. So that's 1.48 times 0.0025. It's going to be pretty small. What's that equal to, please? Minus 3 Newton meters. Okay. B. The student wishes to increase the torque, therefore they increase the number of windings from 1 to 10. What's the torque now? So the torque will be 10 times bigger because the N is a 10 in the formula. So that's 10 to the minus 2 now. Okay, the current is increased by 10 and the voltage is decreased by 10. What is the torque now? I increase the current by 10. So the torque now would be multiplied by 10 again. So that's 0.37 Newton meters. Yeah. It doesn't actually. Yeah. That was the point I was making with this one. There is a small problem though. You can't keep increasing the current and reducing the voltage to get more torque. Because what will happen is you must remember the copper wire has a resistance in it. Now, because it's a conductor, the resistance is quite small, but it still has a resistance in it. And you know the formula for resistance is equal to rho L over A. Yeah? So, there's some wasted heat that comes off here, and what would that equal to? Well, you know that power, if I have my VIR triangle, power equals IV, but I is equal to, V is equal to IR. So this is equal to I squared R, which is equal to I squared rho L over A. So if you increase the current, that's fine, you do get more torque. However, you produce more heat into the copper. So because energy is conserved, you get less power because you're wasting some as heat. So in other words, if you increase the I, then you increase the heat. And you have this formula here to calculate how much resistance is in the copper wire. You kind of notice this not just with electric engines, but really any type of engine. There's a balance. If you try to make your car have more power, then that comes at the price of having a slower maximum speed. If you try to make the car have a bigger maximum speed, that comes at the price of having less acceleration, less power. So it's a bit here with the resistor as well. If you try to make the torque greater, so there's more turning force, that comes at the expense of producing more heat and wasting energy. So you drop the efficiency. So here it's like torque and efficiency. You can increase the torque, but you reduce the efficiency, and vice versa. Yeah. So the answer for the last one is I squared rho L over A is the heat energy. Okay. Apart from question 4, that wasn't too difficult. Now we'll go on to the induction one next. Can I close this?
Sure.
Yeah. Okay.